suppose I have a quadratic equation. In standard form, it's written ax squared plus bx plus c equals 0. Now, it's very important that a, b, and c be real and that a not equal 0. Otherwise, of course, we have a linear equation. When I say standard form, I'm going to want it with the equal sign there and equal to 0. So I'm going to want all the constants and everything on the left side. And then I also want it in descending order of powers. So the x squared first, then the x term, and then the constant term. Now, the zero factor property says if a and b are complex numbers and a times b is 0, then either a is 0 or b is 0, or they're both 0. Now remember, when I say complex numbers, this also takes into account real numbers, where the complex part is 0. Now, suppose I wanted to solve 10x squared plus x minus 2 is equal to 0. I need to factor this. What multiplies to be what? Negative 20 and adds to be positive 1. If I factor this out, I see that my two terms are 2x plus 1 and 5x minus 2. And we've already done factoring. So using the zero factor property, this means that either 2x plus 1 is equal to 0, or, and that or is very important, 5x minus 2 is equal to 0. So you fully factor first and then set each term equal to 0. Now I'm going to solve for x. So 2x is equal to negative 1, or 5x is equal to 2, and you can do these as two separate problems. So x is negative 1/2, or x is 2/5. Now I want to check. In order to check, I put both solutions in, both the minus 1/2 and the 2/5, and I algebraically step them down, and I get the true statement that 0 is equal to 0. So now I'm able to say that the solution set is minus 1/2, 2/5. Now, the square root property tells me that if I have x squared is equal to k, then I can subtract k from both sides. So I have x squared minus k is 0. So now I have a difference of squares. So I can factor this as x minus the square root of k plus times x plus the square root of k. And once I have it factored, I can set each factor equal to 0. And so I have x minus k is equal to 0, or x plus k is equal to 0. And solving, I get x is equal to k, or x is equal to minus k. So we just proved that x squared equal to k is plus or minus the square root of k. That is the square root property. So we say that the solution set of x squared is equal to k is k or negative k. And we abbreviate that with the plus or minus symbol here. The plus or minus the square root of k. Now, both solutions are real if k is positive. If k is negative, then we have imaginary solutions. And you can write it as plus or minus I, the square root of the absolute value of k, but I'm not going to be that picky. If k is 0, then we only have the solution 0, and we call this a double root or a double solution. So if I wanted you to solve each quadratic, then at this point in time, it should become pretty straightforward. X squared is 29 becomes plus or minus the square root of 29. B is x squared is equal to negative 144. Well, that's plus or minus 12i. So don't forget the plus or minus. The negative gives you the I, and the square root of 144 is 12. C is going to be a little bit more work. X minus 8 squared is 24. Square root both sides, you're going to get plus or minus the square root of 24. And we want to simplify that square root of 24 to 2 times 6. So that becomes plus or minus, 4 times 6. So it becomes plus or minus 2 times the square root of 6. I still want to solve for x. I add 8 to both sides. So x is 8 plus or minus 2 square root of 6. Now notice, had you oiled this out, added to 24 to the other side, and used quadratic formula, you would have gotten this exact answer as well. So suppose we want to solve a quadratic equation using completing the square. Well, if a is not equal to 1, then you need to divide each side through by a. First step, always get the coefficient of the x squared term to be 1. Now, you want to rewrite the equation so the constant term is on the other side of the equation. It's all by itself. And then take the middle term, divide by 2, square it, and add that to both sides. Then you'll factor the left side as a perfect square trinomial. And then you'll use the square root property to complete the solution. This sounds really complex, but after you do it a few times, it's pretty straightforward. So let's solve x squared plus 10x minus 20 is equal to 0. The coefficient of the x squared term is already 1. So we're going to put the 20 on the other side. So we're getting the constant on the right side of the equation. And now we're going to focus on completing the square of the x squared minus x squared plus 10. So we're going to take the 10, divide it by 2, and square it, and add it to both sides. So 10 divided by 2 is 5, squared is 25. So we're going to add 25 to both sides of the equation. So this becomes x squared plus 10x plus 25 is equal to 20 plus 25. Now the left side is a perfect square trinomial. So the left side becomes x plus 5 squared. And then when I add 20 and 25, I get 45. Now I can use the square root property so that I get x plus 5 is equal to the plus or minus the square root of 45. And solve for x. So x is negative 5 plus or minus the square root of 45. But I can simplify the 45 as 9 times 5. So this becomes 3 times the square root of 5. So your answer is x is equal to negative 5 plus or minus 3 times the square root of 5. And you can write it in solution set notation, negative 5 plus or minus 3 root 5. Now for this one, I want to solve it by completing the square, but my leading term is not 1. So I need to divide everything through by 4. So when I do that, I get fractions, but that's all right. Now we're going to take the 5/4, and we're going to move it to the other side so it's by itself. We're going to take the middle term, divide by 2, and square it, and add it to both sides. So 6 divided by 4 simplifies into 3 halves. So when I take 3 halves divided by 2, that's 3/9 squared. 3/4 squared is 9/16. So I'm going to add 9/16 to both sides. So this becomes x squared plus 3 halves x plus 9/16 is equal to negative 5/4 plus 9/16. Now my left side is a perfect, and now we're going to factor. We have a perfect square trinomial. So this becomes x plus 3/4 squared is equal to negative 11 over 16. I'm going to use the square root property so that this becomes x plus 3/4 is plus or minus I times the square root of 11 over 16. And then I'm going to add the 3/4 to the other side. So x is negative 3/4 plus or minus I square root of 11 over 16. Now I do need to simplify this so that I don't have a radical in the denominator. Square root of 11/16 is the square root of 11 over 4. So my solution set is minus 3/4 plus or minus the square root of 11/4 I. Now the quadratic equation is, you learn this in Algebra 2. If you have ax squared plus bx is equal to 0, then the quadratic formula gives you the solutions. X is minus b plus or minus the square root of b squared minus 4ac all over 2a. Now you want to make sure you extend that bar. A lot of students just have the 2a over the square root of b squared minus 4ac. So make sure you extend that fraction bar completely. So suppose I wanted to solve x squared plus 6x equals 3. The first thing I need to do is write it in standard form. So I add negative 3 to both sides to get x squared plus 6x minus 3 is equal to 0. In this case, a is 1, B is 6, and C is negative 3. If you're practicing this, you may want to actually write those out to start with. So substituting into the equation, substitute it in exactly. I need to see the negative where the negatives are, even if it becomes positive. So it's going to be negative 6 plus or minus the square root of 6 squared minus 4 times A, which is 1, times C, which is negative 3, all over 2 times 1. On your papers, I need to see this exactly as this is with the parentheses and the values plugged in. Now, all right, so this is negative 6 plus or minus the square root of 36 plus 12 over 2. Simplifying inside my radical, I get the square root of 48. Now I know that that's 48 is 16 times 3. So this becomes negative 6 plus or minus 4 times the square root of 3 divided by 2. And we need to further simplify, factor a 2 out of the negative 6 and the 4, so we can cancel with our denominator. So the answer is negative 3 plus or minus 2 square root of 3. And you can put it into the solution set notation. Now suppose I wanted to solve 4x squared is equal to 3x minus 5. First thing I need to do is put it in standard form. So I subtract 3x minus 5 from both sides. So I get 4x squared minus 3x plus 5 is 0. Now, in this case, A is 4, B is negative 3, and C is 5. You're going to substitute directly into the quadratic formula. Do your algebra. And only once you get negative times negative 3 do I want you to put the positive there. Again, I need to see that step. Negative 3 squared is, of course, positive 9, and this is minus 80 divided by 8. So this becomes 3 plus or minus the square root of negative 71 divided by 8. So I need to rewrite this as a complex number. And so my solution set is 3/8 plus or minus the square root of 71/8 I. Now, what do you do when you have a cubic equation? Well, you remember you can use, remember how to factor a cubic. This becomes x cubed minus 25 is x minus 5 times x squared plus 5x plus 25. And so the linear part's already factored for you. So x minus 5 is 0, or x squared plus 5x plus 25 is 0. So you use the zero factor property to get yourself down to your quadratic. So here, A is 1, B is 5, and C is 25. So when I substitute in, I get negative 5 plus or minus the square root of 25 minus 100 divided by 2, or negative 5 plus or minus the square root of negative 75 divided by 2, or negative 5 plus or minus 5i square root of 3 over 2. And the whole thing is over 2. So my solution set is 5 and negative 5 halves plus or minus 5 root 3 over 2i. Now, suppose I want to solve the equation v is equal to 1/3 pi r squared h for r. Then the first thing you want to do is find your variable in there. So it's this r squared. We want to isolate the r. So I'm going to multiply both sides through by 3 and then divide by pi h. So I have r squared is 3b divided by pi h. So when I take the square root, I use the square root property. This is plus or minus 3b divided by pi h. But now we don't want radicals in the denominator. So we're going to rationalize the denominator by multiplying by the square root of pi h over the square root of pi h. So we get r is plus or minus the square root of 3b pi h divided by pi h. Now suppose I want to solve 2my squared minus ny is equal to 3p for y. So the first thing you need to do is get it in standard form. And in this case, you're going to use the quadratic formula. Now, this is very ugly because we have variables and not numbers. But A is 2m, B is minus n, and C is minus 3p. So when you substitute this in, you get n plus or minus the square root of n squared minus plus 24mp divided by 4m. The discriminant of the quadratic is what's under this radical. B squared minus 4ac is called the discriminant. Note, the discriminant is b squared minus 4ac, not the square root of b squared minus 4ac. So it's just that part that's under that radical that's your discriminant. Now, if a, b, and c are rational numbers and the discriminant is positive, then you're going to have two solutions. If it is a perfect square, then you have two rational solutions. If it's not a perfect square, then you have two irrational solutions. If the discriminant is 0, you're going to have one double solution, and it's going to be rational. And if it's negative, you're going to have two complex numbers, two complex solutions. Now, the restriction that A, B, and C be rational is very important. Because what if you have the square root of 5 in here? The discriminant is 9, which would indicate you're going to have two rational solutions, but you don't. You wind up with an irrational answer. So they just have to be rational numbers. Suppose I want you to determine the number of distinct solutions and tell me whether they're rational, irrational, or non-real complex. You can do it without actually solving it. As a matter of fact, I want you to do it without actually solving it. I want you to look at the discriminant, which is b squared minus 4ac. So you identify A as 4, B is negative 12, and C is 9. And then b squared minus 4ac is negative 12 squared minus 4 times 9. So that's equal to 0. This tells me that there is one distinct rational solution, and it's a double solution. If I give it to you in non-standard form, then the first thing you need to do is write the quadratic in standard form. Now A is 3, B is 1, C is 5. The discriminant is b squared minus 4ac. It's 1 squared minus 4 times 3 times 5, or negative 59. The discriminant is negative, so I know that I have two distinct complex solutions. Again, for this problem, I need to put it in standard form. So A is 2, B is negative 6, and C is negative 7. The discriminant is b squared minus 4ac, so I get 92. Now, this is two distinct solutions, and you can't take the square root of 92, so they're irrational solutions.